to look at my poster. My topic is boomerang physics. However, to make it a little easier to visualize, I wanted to ask if any of you guys at home have any bananas in your kitchen. So the banana shape is similar to the shape of a boomerang, and it's really nice just to have something in front of you to look at and to spin and to rotate, and that way when I'm explaining the different things, it's easier to visualize. So if you have any bananas in your kitchen, if you can pause the video and then come on back. Okay, thanks for waiting. So I hope you guys do have your banana boomerang. I have mine in front of me. So we'll start off with the physical characteristics of a boomerang. So a boomerang is an aerodynamic object that when thrown at a trajectory that's parallel with the ground, it should reasonably come back to the thrower. So a boomerang is usually made of 2 or 3 wings. So if you look in the picture on the middle right there, it has 2 wings, but sometimes there's 3 wings as well. Each wing is called an airfoil. So if you look at the picture underneath, that's like a side view of the boomerang if you laid it flat and just kind of looked eye level. So it's more curved on the top surface and then more flat on the bottom surface. And that's also like the wings of an airplane. And then to throw the boomerang, so you're going to hold your banana boomerang, if you're right-handed, you're going to hold it between like your pointer finger and your thumb. And you're going to hold it vertically up and down, and then you're going to snap it with your wrist. So not like a frisbee, how you would throw more flat, like a flat pizza, like if you toss a frisbee or a pizza at someone, because that will just shoot up. And then once it stops spinning, it will fall down due to gravity. But throwing it vertically and a little tilted, but we'll get to that in a second, will create that circular path all the way around. So, okay, so when we're holding our banana boomerang, right-handed people will just tilt it a little bit, about 30 degrees clockwise from our vertical position, and then that will give it the correct angle so it spins in the circle, and then it comes back to you, and then when you're ready to catch it, then it comes back flat like a frisbee. And then boomerangs have rotational motion as well as translational motion. So as the boomerang is moving in the air, it's also spinning. So it's spinning while moving. So it has both rotational and translational motion. And if we scroll down a little bit, we have rotational motion. A revolution is one complete rotation around a circle. The rotational velocity is the rate of change of rotational position, and that we use the little omega sign. It's like a little fancy W. And then the rotational acceleration, which is like a little alpha, is the change in rotational velocity during the time interval. Rotational acceleration depends on external net torque and mass and the distribution of that mass with respect to the axis of rotation. So I have this little diagram, and that's my little nutcracker helper. So if we're the thrower, we're the little nutcracker, and we have the boomerang in our right hand, we're going to flick it on our wrist, and then it has that very first initial velocity, the little omega with the arrow in green. And then using the right hand rule, that's how we determine the angular momentum. So we take our right hand again, and if like we're waving to someone, it'll be straight out in front of us, or doing a high five, and then we curl off our fingers around, and then our thumb is pointing to the left. So like inwards towards the circular path. So that's the angular momentum. And then at every little point there's like 1, 2, 3 different little points. The angular velocity is changing in a circular pattern, and then so the angular momentum is also facing inward. So the initial rotational velocity is parallel to the arm when you throw the boomerang, and the rotational momentum is perpendicular to that rotational velocity and faces inward into the circular path. And then when we combine the vectors, so on left of the picture, when we place the initial momentum vector and the second momentum vector tail to tail, we can draw the change in momentum. So that's the delta L right there. And this is called the torque. So during each time interval, the rotational velocity follows a curved path because of the gyroscopic precession. And we'll get to that secondly. So right here, the delta L is equal to the torque. Okay, now we're on to gyroscopic motion. So again, the good old right hand rule. So when you curl your hand around the motion of the boomerang, your thumb will point toward your left or into the middle of the flight path, and like we said, that's the angular momentum. That's the red arrow with the L on it. And then angular momentum is similar to linear momentum, but is the product of velocity and inertia. Rotational inertia is the capital letter I, and it's the location of mass relative to the axis. And it quantifies the ability of an object to spin around a specific axis or the resistance to change in rotational motion. If an object has higher inertia, it's harder to change its rotational motion. And then torque is similar to force, and it measures how much a force causes the object to rotate about the axis. Rotational acceleration is directly proportional to torque produced and inversely proportional to the mass times the distance between the object and the axis squared. So looking at the three diagrams to the right, we have a couple different axes. We have the X, Y, and Z. So if you're holding your banana boomerang, the X, you're gonna like hold it straight in front of you up and down and then turn it. And then, so that's one way. And then if you hold the banana again and you're gonna turn it the other way, so like one way is vertically and then one is horizontally. And then the other way is the way you would throw the boomerang. So that has the highest inertia and it just spins instead of twists. And then to the right, there's some more pictures about different planes and stuff. But it's also really cool to visualize like with your banana boomerang, because that way it's easier to kind of see the way it's turning. So using Newton's second law, we can compare the linear momentum and angular momentum as well as force and torque. So inertia is comparable to mass in the P equals mv equation, but with an importance on the distribution of that mass. So using the fundamental equation, force equals mass times acceleration, we can rewrite that as force equals the change in linear momentum divided by the time interval. And then on the right side equations, I have torque is equal to delta L over delta T. So that's going to be the change in rotational momentum divided by the time interval. So torque is the force causing the boomerang to change orientation at each position and creates a curved flight path. And then also, you got to throw lift in there as well. So similar like how airplanes have lift, the boomerang does as well. So the boomerang is moving forward while it's rotating. So remember we said it had translational motion and rotational motion. So this creates like an imbalance of the lift forces on the blade. So if you look at the picture to the right, the top blade does have a larger lift force, which makes it spin faster at the top. And then so the bottom blade has a smaller lift force, which makes it fly slower. So this imbalance makes it speed up as it's going. So as it's spinning in the air, the boomerang tends to turn inwards, and that creates that circular path. And then again, using the right hand rule, it goes towards the center of the path. Our thumbs point toward us, and that's perpendicular to the momentum and opposite of the angular velocity. And due to that torque, the boomerang precesses, which means that it continuously changes its axis of spin. So precession is a change in orientation of the rotation axis of a rotating object. So the boomerang continues these really small adjustments every single point until it creates that circular flight path and then returns to the thrower. So thank you guys so much. I hope you enjoyed a little bit about boomerangs, and now you can kind of understand a better idea about how they work if you see one. Thank you so much. Bye-bye.